the angle of the twist is and again, for the first time, we look at this equation. This equation basically tells us the relation between the torque and the angle of the twist. And if you recall our old stuff in traditional mechanical material, we know that the P equal to T L over Gj. So that is the equation we studied for the circular shaft. So here we have torque, and then we have the angle of the twist speed, and that is regarding to the dimension and the material properties. Similar to this one, we have those equations for the thin wall shaft and arbitrary cross section. And so from here you can compare the TL play the same role as the TL, and G, we have G here. So J for this quantity and apply to the non-regular cross section of the thin wall. Basically, J is play the same role as 4A squared and with this one. Okay, so hopefully it can get you kind of comparison and to see what we are doing here. And so for this case, right now you can see A squared, basically A is an area. So basically this term has the dimension to the fourth power. And now we look at this one, this kind of weird integration. Basically it's saying is this. We do the integral, we look at here. The ds means the line integral along the path that make a one circle of the cross section. And divided by t, because t is the thickness and vary. So at a different location, for example, if we take this point as our starting point to quantify our movement of the s. So at this position, then t should be the function of where we locate. So that's a t as a function of the s. So that basically meaning the t thickness is a function of the location on the cross section. So ds over t. So that means simply we want to do the integral. Line integral is per that information. And that one, if we are given more precise information about the thickness, about this function, so basically here, this one, if we would know on one side, in general, if we would know the t as a function of s, for example, I just make any arbitrary. So if say ts will be equal to say 1 minus 2s, whatever. So in this way, you can say that integral basically reduced into this one. So for this one, then you can proceed. I think this one, I think you can utilize the trigonometry kind of skills. You can proceed the integration. Okay. So here I just want to mention to you, this one we can calculate it out. We can calculate, we can compute. And for many exercise problems, and usually our geometry is kind of the regular shape, and the thickness usually is constant on one side, and then changing the thickness on the other side. So basically this one can be decomposed into the summation of a few pieces, and then each piece is simply algebraic calculation. So later on, once we do the example, you will see. Okay. So that is the formula for these properties, and how to derive this formula. And here is the little bit detail, and allow me now to write it up. Basically, the formulation, and again, the formulation leading to that result is not given in our textbook, so I will not to write it up again. But here is the result here, and to reach that result, and based upon is the energy equilibrium of conservation of the energy, and that means is this: we apply a torque. We apply, and the shaft will be strained, will be deformed. That means strained. So that will store strain energy there. The energy stored there will be equal to the torque, the work we apply. right? And the work basically is torque multiplied with corresponding distance, which means the torque multiplied with angle of the twist per se. Okay, so one half, that is the equilibrium quasi-static process of the work applications. And the strain energy is in terms of this formula. And this formula probably you are not familiar with because I haven't given that to you in ES31. But maybe later we will get familiar with. But anyhow, that is a form of the strain energy. And then the two terms must be equal. And this one, phi, has been given by the property 2. And then we can implement this integration carefully. Tau, we know that tau can be from property 1. So do a little bit arrangement, then we can obtain to that case, like this. So now the remaining issue is we can do certain exercise.
Is that TDS or is that tau ds? For your stored energy.
This is the, let me write it out.
Well, that's tau, but I'm talking about inside that.
T dot ds, T
T
times ds.
Okay.
Yeah, T times ds. In ES31, I skipped the energy, strain energy chapters, but here I would have give you some certain review. Okay, so with those things, I will keep this one, and then we can take a look at a quick example here. I'm sorry, Sarah. I'm sorry, Sarah. I'm sorry, Sarah.
Don't worry about it.